And then in here, I've just been trying to organize this and to break the problem down into different pieces. For example, this is a piece that knows how to generate the timing, so figuring out when to start displaying some row of LED data, when to stop displaying it, how to sequence the blanking and latching signals that tell the circuitry on the panel how to actually move data around at the right times. And then we've got a buffer, which is a little bit of memory that holds one line of data for long enough that we can scan over it multiple times to do the pulse width modulation or the brightness control modulation. And then line scan actually reads that buffer and sends data out to the RGB port here. And then down here, this is work in progress. This was just kind of a test block that generates this pattern that you're seeing now. This is a new version of that test block written in a more straightforward way, where instead of having to write to memory on its own, so you get a coordinate for X, a coordinate for Y, generate a color. You can take as many clock cycles as you want to do this. You just get this begin pixel when you're starting and strobe this pixel done when you're stopping. The piece that I haven't quite written yet, its job will be to sequence using this multiple times over the course of rendering a line in order to render all the pixels. So simultaneously, while this is being coordinated by some new state machine yet to be written to generate all the pixels, we'll be using the other half of that double buffer, the other line buffer, to scan out all the pixels repeatedly in order to do our modulation. 144 bits. It's a lot of flip-flops though. I mean, I think the overall flow of this is we need to render one pixel from each lane, and then we need to output them. If you have a RAM that you can write this full 24-bit wide value for every lane. In this case, we have 2 lanes. I'm designing this to have support for up to 6 lanes. So you write like 6 24-bit values. Now you have to go through each of those 6 24-bit values and read them just to extract a single bit. Because I'm limiting this to 6 lanes, that means that it takes 6 clock cycles to output every pixel, if I do it that way. I mean, I'm curious to design this with flip-flops. We'll see if it's too big. I don't know if it will be. I think I'm still going to be writing this in Verilog like it's a memory, even if I'm ending up using it kind of like flip-flops. So let's make this 24 bits wide. This will be the pixel buffer. It just stores 1 pixel, but for every lane. So that makes a little memory, which could also be inferred as a bunch of flip-flops. It's normal for you to be able to reinterpret bits in whatever way you want. The thing that is weird about this particular situation is that it's like if I have memory that's a matrix of bits, I need to be able to access that matrix as columns and as rows. That's what's making this strange. So we request the first pixel. When that's done, we write it. If we've got all the lanes, this is where we need to actually write to the RAM. So we're writing first, say, to all the even entries and then all the odd entries. While we're writing all the even entries, we can be reading the odd entries and vice versa. In stuff like this, where I think I'm going to have 2 somewhat independent state machines in this single block that share this little buffer, kind of inferring some logic that might have a common set of either flip-flops or dual port memory. And right now, what I'm trying to do is only take 1 clock cycle per memory cycle to write this out, which in this case means 8 clock cycles per pixel, which is still way faster than our modulation, honestly, so I don't think we really need lots of speed. So then, every clock cycle where the outgoing port is active, we're calculating an address, calculating the data. I actually enjoy arranging schematics. It's like making a pleasing 2-dimensional object is sometimes nice. Whoa! That seems kind of almost working. I mean, that isn't exactly what I was expecting, but it's not completely broken, which is a pleasant surprise. Let's see how big the design is too, like what did all that logic turn into? So we still only have 2 block RAMs, so that big mess that I put in probably just turned into a bunch of flip-flops. We have more flip-flops than before, but it's still pretty small compared to the size of the whole FPGA. Now it's closer to what we had before. Alright, now we have an 8-bit counter that we can control with the buttons. That is an input to our little shader. Output the counter as a color on each primary. Like that. So just a grayscale value that we can increment and decrement. Garbage on the screen momentarily, but I didn't quite catch what it did. Anyway, got a nice black screen scanning out. Right, so that's completely off. That's 1 least significant bit. This is 1 cycle of the modulation, so this represents 1 row, or 1 modulation step for every pixel on that row. So here's 0, here's 1, 2, 3, 4, 5, 6, 7, 8. See? The bits are all a different width, but they are the bits here. That seems right. Let's try counting down from full white. Nice. So we can toggle between green and red. That seems right. That is a little weird. So we got this little glitch down there, and I was expecting one horizontal and one vertical line, not two vertical lines. So like, it may seem like an off by one is not a big deal, but like in hardware design, off by one often means that you're like seriously neglecting to understand the boundary conditions of the problem, which I feel like is what we're dealing with right now. And I think I've made this more complicated than it needs to be because I'm trying to kind of pipeline these loads across rows. Each one of those little blips on D14, those little bursts of clock cycles, that is transferring one row of pixels to the device. And so I'm doing the first one of those after I unblank the display. So the way this works is I always figure out when to unblank the display, and then while I'm kind of exposing that row of pixels to the person's retina, I'm loading the next row of pixels. I think that's probably how it should work though, because that's like the only way I know of to really just keep the display busy 100% of the time. Scanning down 32 rows in the display. Each of those rows we display multiple times in order to display kind of binary code modulated brightness. So we have one bit plane that's weighted to be bit 7. We have one bit plane that's weighted to be bit 6, 5, 4, 3, 2, 1, 0. And those have lengths that are powers of 2. And timing all of that is done with a couple of state machines right now that work together. Some of the bugs are lurking in how those state machines represent their notion of what's current. So we'll need to take a closer look at that. We were using these kind of over-wide counters everywhere. The planes are 3 bits, but rows are 8 bits here. We could support up to 1 256th modulation, which is probably more than you actually want. In this case, we're only doing 1 out of 32 modulation. Like, it seems useful to decide that this module is responsible for doing this one relatively atomic operation, which consists of taking whatever's in the shift registers, latching that, displaying it for a timed duration, and then as soon as the timer is done, stopping the display and then no longer being busy. Begin adder and begin plane should be looked at on the clock cycle when the strobe is set. We're using the plane to set the timer. We're using the adder to directly set the LED adder output latch. You should have a 1 clock cycle latch pulse. It goes high here. On the next clock cycle, we should end up here. That's a little nicer. RGB is 18 bits, which is also pretty arbitrary. That's just to support more panels in parallel than we currently have. So scanning happens per plane, rendering happens per row. We have separate outputs for the row that we're scanning and the row that we're rendering, because those are no longer the same. We also need a toggle output. We have a bunch of outputs that are all pretty similar to each other, but the differences will become important. So this is the current row and plane that we're currently scanning out to the display. It is not necessarily the one we're exposing yet. After the scan out, then we kind of queue up an exposure operation and send that. And then we have rendering, which is yet another thing. You need to render the row, then scan out every plane inside that row. That's all in this LED exposure module now, or expose. Okay, so expose gets a plane and an address from the refresh controller. So we could approach this in various ways, try to test the individual pieces on their own. We're not seeing the addresses come out. Instead of seeing those two lower edges at the same time, we'll see the latch pulse end, and then it'll go into exposure. Yeah, just like that. Now, oh, D7 is now 2 clock cycles long. Is that going to be a problem? This edge right here on D7, the red trace, that is coming from scan begin being set to 1, because at this point it has rendered as 1, so we're actually beginning the scan. This is the next clock cycle at the beginning. We're still asserting scan again because scan busy has not yet had time to go from 0 to 1. It'll take 1 cycle of latency for the other module to actually start. Okay, that looks right. The thing that I'm noticing now, which is causing me to go, is that this and this are now really too close to each other. So this should move that pulse train right by 1 clock cycle. Yes, that's what I wanted. Okay, so the addresses are not changing, like, so it's not scanning, obviously, but the timing of those blanking periods looks right, so that's nice at least. Oh, this is backwards. That's better. Cool, there's the whole refresh. There's 1 frame again. So 1, 2, 3, 4, 5, 6, 7, 8. 99.85 duty cycle. If we zoom in, so we're only looking at this, it's like 84%. So same idea here, except instead of a 3-bit or 4-bit brightness or whatever I was using there, it's 8 bits. So what we're seeing there, that bit that showed up on D0 and D4, if we zoom in, we'll actually see that that's actually a 1 bit for that entire row. This chunk of clock cycles on D14, which is second from the top, that represents 1 row of 64 pixels going out to the display. This change from 0 to 1, that's almost right, but what we're doing here is that's actually clocking out the row that will be illuminated right there. And that's actually not the least significant bit, that's the second least significant. And that could just be a matter of having LED refresh have 2 outputs, so there's scan plane and expose plane. Yeah, I think refresh just needs separate outputs for scan, render, and expose. Okay, expose begin, expose plane, and expose row. Okay, this whole branch happens for 1 clock cycle, and then we just end up right back up here. Okay, so we start an exposure only if we've successfully done the scanning cycle. Okay. Oh, that looks right. That's the least significant bit. It's dimmer than we were seeing before, and it's showing up to the left of that scope trigger. That's the second bit. Bit 0 is much wider than the other bits. I mean, it just looks that way because it's actually bit 7 that's wider, but we're sending bit 0 while bit 7 is being exposed. Testing it kind of anxiously here, but I think it might be all right. This is looking right so far. Great, that's full red. This is finally looking right. Refactoring and some fixes for off-by-1 bugs, and the binary code modulation seems good now. The name for this is Hub75, but I don't know where that really comes from. It's really just a multiplexed LED matrix with a blanking signal, a binary selector for which row you're displaying, and then SPI data driving a bunch of constant current drivers for that row. So it's like a pretty generic strategy. You could drive these in many different ways. I'm driving it with binary code modulation, which is probably pretty popular. Each of those ticks where you see D8 incrementing, that's 1 row. D8 through D11 and D15 are the address lines, so it's cycling through 32 rows. And then those 6 lines at the bottom are data. I'm actually sending it grayscale values by displaying each row 8 times with a different duration for each time, and then I pick a different bit plane. The durations are powers of 2. We could just do something where we have maybe a gradient background and then a crosshair. It does seem like there's a problem with the upper versus lower displays, like that shouldn't be discontiguous there. I don't know what's going on with the top and bottom sections of the screen. There's like a weird 1 pixel offset on the bottom, and we're seeing 1 bright pixel down here right now. Yeah, I think we just need RGB enable and scan data to be delayed by a cycle. Like, pixel counter is the count that we're giving to the RAM. The RAM takes a cycle. Mostly what I changed here is just adding 0 of delay to correspond with the clock cycle of delay that happens in the memory on the addressing side of this. All right, that's the new scanner. We're still using this debug module, which replaces the buffer. So if this works, I'm expecting that purple line to move 1 pixel over to the edge of the screen. I think that's right. So this is with the addressing and LED line scan fixed, and then with the buffer hooked back up. So we're using the dual port RAM buffer again. Okay, so we've still got a problem with the lanes for top and bottom. It really looks like it isn't updating, or it isn't offsetting it by 1 lane, it's updating it by 1 pixel. We're getting close though. So this is while so right here around the cursor, this is while we're exposing the most significant bit. We're scanning out the least significant bit of the next row. And then these pulses are the rendering, which happens simultaneously with that. Oh, that is not right at all. Yeah, D3 is begin pixel, D7 is render write enable. Like, watch that white line kind of go through the shift register. So we can actually have a similar solution here to avoid sending 2 pixel begins. That's a little better. Oh, and that fixed the lane problem. That's good. That's much better. Oh, maybe that was the only bug. Who would have thought? That's much better. I think that's all their addressing being correct. So now in the scope we can actually see the shader operating. So it renders 4 pixels, and then 2 pixels, 2 pixels, 2 pixels. Are those just the 2 lanes, and then there's a delay while we write the data? I think that's what's going on. Stream timing analysis. That tells us how fast the design can run. So like what this is doing in IceTime, it's going through the design and figuring out all the paths that have to happen between, you know, one flip-flop flipping and then that value propagating all the way to all the other flip-flops that have to flip before the clock cycle ends. And by figuring out what the longest path is, that determines how fast the whole design can run. And so this is not as much headroom as I would like. It doesn't seem like it should be failing yet, though. You can see it jump to the other half of the display right there. I'm going to leave these debugs. So these debug signals are now giving us information about the timing of this shader module here. So debug 3 is when we're asking it to begin a pixel, and debug 7 is when it says it's done. So, and then you can see that it's only actually rendering at all for just part of the time. This is when the rendering starts, this is when the rendering stops, and then all of this is blank time until the next rendering. So, and what it's doing is it's filling RAM with all the pixel values for 2 lines on each half of the display. Once it's done that, it goes idle until it needs 2 more lines. Thomas is asking about the colors. So I think these are in BGR order right now, the way they're written. So X and Y would be green and blue, and then the red is now connected to the frame timer. That looks right. It looks a little weird on there because of the interference with the refresh. It looks totally smooth in person. I wonder if I can adjust this so the refresh looks less weird. Anyway, I think this test pattern is good. This is doing everything I hoped for, really. I think I want to make one thing that's basically everything here except for the parts that are specific to the size of the LED display, and then something else that is specific to a 64x64 matrix. So this is now the kind of basic generic LED controller module. We have a line buffer, a scan out module that sends the line buffer over SPI. We have a renderer module that fills the line buffer by interacting with the shader. We have a refresh module that generates all the counters and timing signals. And then we have the exposure module that actually generates the timed blanking pulses and handles latching and all that. Okay, so this is mostly just turning into a pass-through module, but there are a couple of important things to change. There's the addressing block, and then I need to shrink a couple of these buses. In fact, I could have copy-pasted some of that. Yeah, so LED adder is going to be only 32, and then the LED RGB goes down from 18 to 6. So if we wanted to make a module that could scan out, say, several simultaneous 64x64s, or a couple of 64x64s daisy-chained to each other, or some combination of the two, then you can make a different version of this module that makes those decisions. But as it is, this is where I hard-code my 64x64 panel right here. Frame begin and begin pixel. It's the generic LED matrix thing, a bunch of preset parameters, some inputs and outputs. These things make the outputs narrower. This is the 64x64 addressing module. Alright, these are the FPGA outputs that actually connect to the LED panel. And then X, Y, frame begin, begin pixel, pixel done, and RGB are for synchronizing with the thing that's generating content for the display. Okay, so that's a frame counter. That's like a user counter. Okay, so we've got one debug pin for pixel done, one debug pin for frame begin. And otherwise, that's relatively simple. We've got this main LED 64x64 module. It has optional parameters for the number of planes and the LSB duration, which you can use to adjust the brightness modulation. But the default gives you 8-bit color per channel at a reasonable refresh rate of, I think, a couple hundred hertz. Oh, what should we do next on this? I feel like we've finished the driver proper, and now it's time to just make better demos for the driver. I mean, we could try making some patterns that just use the kind of shader interface. We could try making an interface between this and a CPU. And I can imagine doing that a couple different ways, either with like a FIFO queue of pixels to render, or with a frame buffer, depending on how much you want to spend memory and whether the frame buffer is just a useful thing to have anyway. One very simple way to do this, for example, would be to have a memory arbiter that shares one block of memory between a CPU and this pixel shader fetcher thing. And then it would really be treating this as a DMA cycle, where you DMA all the pixels you want for one row, and then you leave main memory alone, and you're using this little row buffer for the grayscale modulation. And that means that accesses to main memory from the CPU might change how long it takes for the row to fetch. But as long as it doesn't take too long, then it doesn't matter. Alright, this is what we've got. Scanlime/iCEBreaker Icestudio LED matrix. Just committed the working high-level example. So yeah, all these .ice files are modules that you can load in Icestudio. They're internally JSON, sometimes with Verilog chunks embedded. Each one of these actually includes a copy of any modules it depends on, so you can use them independently. If you have a 64x64 matrix, for example, you could just grab just this LED demo.ice and hack on that without having to download these dependent modules separately.